Okay, welcome everybody to this new DAI seminar. Today our first speaker is Paulo Varandas from the Universidade de Aveiro. I'm very happy that he will give this talk that will be on the decay of correlations for codimension-one hyperbolic attractors. This DAI seminar. So thanks, Paulo, please.
Okay, so thank you very much, Claudio, for the invitation, for the presentation. So today I'll talk about decay of correlations for attractors. This is a keyword, hyperbolic attractors, and second keyword is codimension-one. This will appear soon. And okay, so the organization of this talk is that first I'll spend some time, since I'm the first speaker of the day, which both two topics on decay of correlations for flows. I'll spend some time introducing some basic notions, setting some notation, and I will make some historical background on the topic. And then I'll state the main results, which were obtained some time ago with a former PhD student, Diego Daltro. And then I'll say some words about the ingredients in the proofs, even though it's a little bit technical, so I'll try to grasp some of the key ideas and finish with some questions which are still unknown.
Excuse me, Paul, because before you start, let me just recall that I forgot to say that we are streaming on YouTube, so everyone is welcome to ask questions during the talks. But if you don't want to appear on the screen on YouTube, you can also write your questions in the chat, and I will read it for the speaker. Okay, thanks.
Great.
Please.
Thanks. Okay, so the setting will be that I'll always be thinking about compact Riemannian manifolds, and I'll denote by xt the C1 flow on it. And a hyperbolic set is just a set which is flow invariant, and for which there exists a dxt invariant splitting in three directions, one of which, along which you have exponential contraction for positive time, one on which you have exponential contraction in backwards time, which is this condition B, and one which is just the direction generated by the vector field. So hyperbolic flows or hyperbolic sets have been very much well studied, and you say that lambda is a basic set if it is transitive and maximal invariant, meaning that there exists an isolating neighborhood U containing it such that lambda coincides with a set of points which never leave the set U either for positive or negative time. And we say that the set is an attractor if it is transitive and there is an isolating neighborhood which attracts all formed by points which get attracted to lambda. That is to say that lambda is this intersection positive time of the images of U. And a flow is axiom A. Sometimes people just refer to it as hyperbolic. If non-wandering set is hyperbolic, and the non-wandering set is the closure of the critical elements. And here, by critical elements, I mean singularities and periodic orbits. Of course, if it's hyperbolic, then singularities should be isolated. And Smale's spectral decomposition theorem says that if you have a hyperbolic axiom A flow, then the non-wandering set can be written as a finite disjoint union of hyperbolic basic sets. So if you want to understand the ergodic theory of such flows, you may well understand the ergodic theory of each individual piece. So for that reason, you can always start to think about what happens with the ergodic aspects of hyperbolic basic pieces. And from the geometric point of view, so these invariant subbundles, they are integrable. This gives rise to existence of stable manifolds and unstable manifolds, which have been used in the 70s to build what's called Markov partitions, which allow to code the dynamics with symbolic dynamics. So in the early 70s, works by Bowen and by Ratner allow to build what are called Markov partitions for flows. One constructed for hyperbolic basic sets, the other for ANOVA flows. And these can be read as follows. So if you have D on a manifold to be a local cross-section, a set R within this local cross-section and formed by points in the hyperbolic set is called a rectangle if you have a local product structure, meaning that so there is this issue for flows that you always have the flow direction. So if you want to talk about local product structure, it should be up to a displacement along the orbits of the flow. For that reason, you always consider center stable manifolds, which are saturated of stable manifolds along the flow direction. And you take center unstable manifolds, and you say that a set has local product structure or is a rectangle if exactly for any 2 points in R, when you take center stable and center unstable, they will cross exactly in 1 point, which belongs to the rectangle. And a collection of rectangles is called a proper family if I will just stick with this condition, which is easier to represent, is that this rectangle serves as a set along which you can cover the manifold by certain flow boxes. So this is to say that if you take any of such rectangles, if you flow it in, say, negative time, then this will cover the entire set. And using this property, you can build a global cross-section to your flow, to your hyperbolic basic piece, which is just the union of the rectangles. You can define what is your Poincare first return map, to first return time, which is the time that the point needs to go from one rectangle, one cross-section to another, and define a Poincare first return map. Well, these maps are continuous in the interior of the rectangles, but they may lead to discontinuities. And let me just show you a representative picture. Is as follows. So these are representing cross sections to the flow. So the vertical direction represents the flow direction. On the x direction, you have stable direction. So rectangles are just shrinked in this x direction. They are expanded in the y direction, and they are moved upwards with the flow direction. So it means that if you have this cross section, then there are points on the left which will meet this other cross section D2, points on the right meet this cross section D3, and points here in the middle, they create discontinuities. And these will lead to appearance of discontinuities, as I will just soon mention. And a proper family is Markov if the Poincare map is a Markov map. So it means that every time that you, in the stable manifold, in the stable direction, sets are mapped inside the stable boundary, and then the unstable, you have some covering property along the unstable direction. And in 73, Bowen proved this nice result that a hyperbolic basic set for a C1 flow is semi-conjugate to a suspension flow over a topologically mixing shift of finite type. So This means that from the topological point of view, it's kind of indistinguishable if you look at a hyperbolic basic set and the action of the flow inside, and a suspension flow where the base dynamics is just a topological mixing subshift of finite type, which are very well understood, and you have some roof function associated to it. So the flow is in these coordinates, it's just displacement in the time coordinate, and in the first coordinate, when you get to the top, you identify this point on the top with the action of the shift. Great, and this was useful to study the ergodic theory in terms of describing equilibrium states for such flows. And this can be, let me just recall some of these notions. So for a compact metric space and a continuous map and a potential, you have the classical variational principle. So the topological pressure is just the supremum of free energies, which is the Kolmogorov entropy plus the time averages of mu. And an equilibrium state is just a probability measure which attains this equality. And for flows, it has been defined these objects like using the time one map. So the topological, you say that mu is an equilibrium state if the topological pressure, when computed for the time one map, coincides with the entropy of the measure for the time one map plus time space averages. What happens is that time one maps of hyperbolic flows, they are no longer hyperbolic, they are partially hyperbolic, and they are really hard to, in some senses, to understand. And for that reason, the previous formulation seemed kind of easier in terms of reduction from continuous time to discrete time. And this was the content of this paper by Bowen and Rell, and also Hayden in 93, adding something here, which mentions that every Hölder continuous potential admits a unique equilibrium state, and it is actually a Gibbs measure. So what is the idea? The idea is that once you are giving let's think in the case of suspension flows, which they are semi-conjugate to the original flow. So if you want to reduce to a potential for discrete dynamics, you just integrate your potential along the flow direction until you get to the top under the roof function. Then you get a potential on the two-sided shift. You use uniform contraction to solve a cohomological equation, making the potential depending only on future coordinates. And now, since you reduce the dynamics to a one-sided shift, then you have uniform expansion, for which you can apply a Gouëzel theorem to build equilibrium states. And these equilibrium states are Gibbs measures. And Gibbs in the sense that if you think about Pn of x like a cylinder of length n centered at x, then the measure of these cylinders can be described up to a constant by exponential of minus n times pressure of the potential plus the Birkhoff sums of this potential along the orbit of the point. And the equilibrium state is the unique invariant measure absolutely continuous with respect to a conformal Gibbs measure. And then you have to make the process back again. What you do is that since the two-sided shift is the natural extension of the one-sided shift, then there exists a unique invariant measure which projects to that one, and then you lift for the flow just taking this usual parameterization like product with Lebesgue and normalize it. And for sure the case of SRB measures, which were the motivating case in the very beginning in Bowen-Gouëzel's paper, are constructed in this way, just taking this potential, which is written here, derivative of minus log Jacobian. in the unstable direction. So in this sense, the topological description using Markov partitions allow to construct equilibrium states, but they don't give a hint about their ergodic statistical properties. And let me just mention one thing here in this construction, is that this potential here, which gets induced on the base, it is only piecewise Hölder continuous. And piecewise Hölder continuous precisely because of this picture that I've shown you here. Because if I integrate a potential along the vertical direction, points on the left get integrated by a much lower roof function than on points on the right. And this is crucial for what happens next, is that these piecewise Hölder continuous potentials, they give rise to equilibrium states that they need not satisfy some geometric measure theory condition known as the Federer property. What is, so I see here a question, what is overlay? If you ask where?
Yes, I think
Yes,
that's the point.
yes, was just not to interrupt you. Third step, there is a unique equilibrium state mu for P bar P or overline P.
Oh, sorry. It's for the pressure. It's a typo. Yeah, for
okay.
the pressure with
Thank you.
respect to this.
Thank you.
With this. Yeah, but feel free to interrupt. It's easier. Thank you, Michele.
You're welcome.
Okay, so studying decay of correlations, you just can define correlation functions by this formula here, which is very well known, which just measures the asymptotic independence of the observables V and W composed with the flow. And so if the measure is mixing, this tends to 0, and you are interested in understanding at which speed this happens for classes of observables. And we will say that mu has exponential decay of correlations if these correlation functions, they decay like an exponential times the product of the norms of each of the observables in Hölder condition. This is the Hölder norm of the observables. I will always think about Hölder observables. So let me just give a brief background on the topic. So the first kind of striking result in comparison to what is known for discrete time was a paper by Gouëzel in 1983 and another by Polycott in 1985, which showed that mixing rates for Axiom A flows can be arbitrarily slow. So they constructed suspension flows over hyperbolic sets with piecewise constant roof function, just two roof functions. One is 1, constant to 1, other is a parameter alpha. And depending on the alpha, you have mixing, but you don't have exponential mixing, and mixing can be arbitrarily slow. And so this gives a first counterexample showing that hyperbolic basic sets can have very slow mixing, but this is not for attractors. This is for basic sets of horseshoe type. Then in 1998, Dolgopyat proved that rapid mixing, so mixing which is faster than any polynomial, is prevalent for parameterized families of Axiom A flows. And Field, Melbourne, and Torok in 2007, they proved that most hyperbolic flows, so C2 open and CR dense Axiom A flows, they have that each non-trivial basic set is rapid mixing. This was proven based on certain Diophantine conditions on periods of periodic orbits, which cause this fast mixing, rapid mixing. But for exponential decay of correlations, this came in 98 by a marvelous paper by Dolgopyat, which brought a new approach to study decay of correlations for flows using Paley-Wiener theory. And what it proved is that if you have an ANOSA flow, a transitive ANOSA flow, C2 plus epsilon, such that both stable and unstable foliations are C1 smooth, so this is a rigid condition, which are jointly non-integrable, then they decay exponentially fast with respect to all equilibrium states. Later, Polycott used the same strategy as Dolgopyat to show that for certain equilibrium states and certain Axiom A flows, the same thing holds. And Liverani proved exponential mixing for contact ANOSA flows. Other results by Stoyanov give some conditions under which the equilibrium states can also mix exponentially. But in all of these results, these classes of flows, they don't form open sets of hyperbolic flows. So this is the C1 stable and C1 unstable foliations. This is a non-generic condition. Being a contact ANOSA flow is a non-generic condition, and so on. So the point is that people started to believe, and sometimes it's mentioned as a Bowen-Gouëzel conjecture, that ANOSA flows have exponential mixing, provided they are topological mixing. That every topologically mixing ANOSA flow should be exponentially mixing. This is still an open problem. And building over this strategy of Dolgopyat, several people started to give criteria for exponential decay of correlations. Baladi and Vallée, Avila, Gouëzel, and Yoccoz, and Araújo and Melbourne, they gave criteria for decay of correlations for suspension flows. I will mention these in one minute. And using these criteria, several people gave first examples of hyperbolic attractors and even ANOSA flows which mix exponentially fast. Still, the conjecture is not completely is not known if it is true or not, but Suji and Zhang gave a proof that three-dimensional C-infinity mixing ANOSA flows have exponential decay of correlations for all equilibrium states, and there are related results by myself and Melbourne, which help to verify conditions for decay of correlations, like building Markov extensions or Gibbs Markov maps for Axiom A flows in arbitrary codimension. But what I want to stress is that after this pioneer result by Dolgopyat, this group of people, they brought several criteria which are extremely useful for studying decay of correlations, and this is what one of the cornerstones in what I'll talk in a minute. So what is the criteria? So the criteria can be thought as follows. Assume that you have a suspension semiflow over a C1 plus alpha hyperbolic skew product and the piecewise C1 good roof function. Then you have exponential decay of correlations. So the base map should have some hyperbolicity and the roof function should be good. So hyperbolicity of the base map means that it can be written in a system of coordinates as a skew product. The first map is a C1 plus alpha piecewise expanding Markov map. The second map has fiber-wise contraction. So this is a contraction, so meaning that if you fix the fiber in the first coordinate, the distance between these points gets contracted exponentially. So you have a uniform contraction on the second coordinate. And that the measure that you are studying, in case the SRB measure here, that it admits a good disintegration, meaning that if you use Hoechling's disintegration theorem to decompose the measure on the product space as measures on the fibers times a measure on the unstable direction, then this disintegration, when you vary the point on the base, then this integration varies Hölder continuously, and the formulation for the Hölder continuous variation is this one, is that for Hölder continuous observables, the integral varies Hölder continuously. And this allows to make a reduction from observables on the phase space, both coordinates for observables just on the unstable direction. So this is the notion of what you aim at having as a base map for the suspension flow. And a good roof function is a roof function which is constant along stable manifolds. You don't want it to depend on stable manifolds. That it has exponential tails with respect to Lebesgue. If you are looking at SRB measure, Lebesgue becomes the relevant measure. So you could replace here by the conformal measure if you're thinking about other equilibrium states, but in case of SRB measure, it's just that Lebesgue measure has exponential tails. That the roof function can grow, but it is compensated, the growth of the roof function is compensated by the derivative of inverse branches of f, and that the roof function, if you expect to have mixing, you cannot have a constant roof function, because otherwise it wouldn't be even mixing. And if you aim at having exponential mixing, it's somehow natural to expect that the roof function is not homologous to a piecewise constant roof function. This is the uniform non-integrability condition in this framework. Okay, so this is the criteria that one often tries to use to prove exponential decay of correlations for flows. And in the first result that prompted the criteria as this, Baladi and Vallée highlighted the point is that in several arguments, people were misusing that the equilibrium states would necessarily satisfy the Federer property. So what is the Federer property, or the doubling property for a measure? It asserts that if you compute the measure of a ball of twice the radius, it is bounded above by a constant times the measure of the initial radius. And this property here, it is satisfied for Lebesgue measure. And if it is satisfied for Lebesgue measure, it is also satisfied for measures which are absolutely continuous with respect to Lebesgue, in particular, which have bounded densities. So in particular, in these cases, when you were interested in studying decay of correlations for SRB measures, this property was satisfied immediately. However, Gibbs measures associated to piecewise Hölder continuous potentials, as the ones that appear when you make suspensions of flows, then they need not satisfy the Federer property. So this creates this issue that how to overcome the lack of this property in order to prove exponential decay of correlations using this kind of criteria. And this was the problem that myself and Diego were looking at some time ago. So the results can be read as follows. If you have a C1 plus alpha flow and lambda a codimension-one hyperbolic attractor, so you have a one-dimensional unstable manifold, and the stable bundle is C1 plus alpha, then if you have topological mixing, then you have exponential mixing. And what we prove is that if stable and unstable subbundles are not integrable, then you have exponential mixing with respect to all equilibrium states. So we have this is a version of what one expects, is that hyperbolic attractors, they do have this kind of dichotomy, that either you don't mix topologically, or if you mix topologically, then you should have exponential mixing. And after constructions with Vitor and with Oliver, we are able to build manifolds which generate which realize these kinds of attractors, which mix exponentially. And the part of the construction on which you obtain this condition is that you ask for some strong bunching condition. So if you aim at building examples that satisfy these assumptions, what you do is that you start with a hyperbolic attractor for a diffeomorphism, which has very strong unstable direction in comparison to the stable direction, and this helps to form a bunching condition, which is represented here in gray. I won't speak much about that, but which allows you to prove that this stable bundle is C1 plus something. If you demand further bunching, you have further regularity. This is the bottom line. And actually this result for hyperbolic flows, in parallel with the theory that I told you that the Bowen and Rel developed, it can be thought about suspension flows. So actually the first theorem is a consequence of this theorem B. It says that if you have given T as a C1 plus alpha piecewise expanding Markov map of the interval, and if you have a suspension semiflow with a roof function, with a good roof function, then if R is homologous to a piecewise constant roof function, or you have exponential mixing for all Gibbs measures. So this is the dichotomy that one has for attractors, that often which is not proved for, which is not true for other hyperbolic basic sets. So let me talk a little bit about the ingredients in the proof. So the ingredients are nowadays well known. So I will focus much more on what we had to develop related to this. So let us focus in the case that T is a piecewise C1 plus alpha expanding map of the interval, denoted by P the finite Markov partition. Let R be the piecewise C1 roof function. So we consider the twisted transfer operator, which is just the transfer operator, the classical Gouëzel transfer operator, where here you introduce a complex parameter S. So you discount S times the roof function, and you take these twisted transfer operators and you normalize them. So for S equals 0, so this is the usual transfer operator, you know how to normalize it. Then you have a spectral gap, Hence, for small parameters, real parameters sigma, you have a leading eigenvalue and a leading eigenfunction, which are still unique. So this leading eigenvalue is the normalization factor. Hence, you can define these normalized transfer operators, which are normalized by the real part of the parameter S times this twisted original transfer operator. So you have this classical formula, and the goal is, after these reductions by Dolgopyat, is that you can get exponential decay of correlations, provided that you have what is called cancellations, and provided that you have a contraction in the L2 norm of the action of the transfer operator, of these twisted transfer operators. So what one aims at is at considering observables such that the Holder constant is small, this represented by such a condition like this, which is a cone condition. So let's say in rough terms is that if you have observables such that the Holder constant is small, meaning that they are nearly flat, nearly constant, then you can produce cancellations in the terms of appearing in the iterates of the Perron-Frobenius operator, meaning that these objects are in different phases. So this represents vectors in the complex plane, because you are introducing a complex number here. So if some summands point in one direction and others point in another direction, the sum of these elements will produce some cancellation and will decrease in norm. So this is the goal. From the technical point of view, the terms that determine the phase are given by R. So when you iterate this transfer operator, what you obtain is the sums of the roof function computed in different points. And these points are given by the pre-images by T. So I'll define by H1 and H2 different inverse branches of the map T to the power n. So this function here, which is just the difference between Birkhoff sums of the roof function in different points, which are pre-images of the point x, they will determine the phase. They will determine in which direction does the vector points. Okay, and we'll say that R satisfies this uniform non-integrability condition if there exists constants D and R positive, and for some sufficiently large n0 and a point y, there exist inverse branches such that y is in the image of this element. So y is the endpoint of some, it has two different inverse branches, along which the infimum of the derivative of this function is larger than d. So what I'm claiming is that if this function here has a derivative which is larger than some constant, it means that you have some positive speed on the directions of which you have the complex parameter, which helps to produce points on which you have different phases. So this is the ingredient. But this is a condition. This is an analytic condition on the roof function, but it can be translated in terms of some geometric aspects. So Butterley and War did this. So they noticed that if you consider a suspension semi-flow over piecewise expanding map, then the base dynamics has domination. So this is dominated because the base dynamics is expanding and the center direction is neutral. Hence, if you take the derivative of this map, it will have this form, and these cones, which are centered on vertical direction, they are preserved. And you can translate transversality. You can translate the uniform non-intrudability condition in terms of a transversality condition and suitable choice of preimages for the transfer operators. So what we proved after this result of Bartley and Bohr is that the uniform non-intrudability condition is actually equivalent to say that specific choices of iterates of the Perron-Frobenius of the twisted transfer operators, they decrease smaller than 1. So we know that the transfer operator is normalized, so its spectral radius is 1. But so here if this slim soup is smaller than 1, it means that for every point you can, and for any preimage, you can find points, actually plenty of them, which are in transversal relation with him, such that this sum is smaller than 1. So it boils down of showing that if you don't have if you are not homologous to a piecewise constant function, then actually you can produce these cancellations. You can produce this this positive derivative here. Okay. And so in a snapshot, what we prove is that under this, if the roof function is not homologous to a piecewise constant roof function, you can always find suitable inverse branches, here represented in green and brown, such that when you take the sums of the roof function along the orbit for the preimages in these different objects, then they produce phases which are farther away, and the sums of these vectors cancel. But where does these kinds of cancellations, these are good, but it doesn't express nothing about the measure. This is just analytic. It says that for any piecewise expanding map, you can, if the roof function is not homologous to piecewise constant, then you can produce points where the derivative is larger than d, which means that you get different phases, but the measure is not entering here. So where does the measure pops up? It pops up in this kind of formula, that for a piecewise Hölder continuous function which has slow slope, so nearly constant, the integral on big sets is comparable to integral in smaller sets. So what does the feather property, why does the feather property is important, is that once you can produce cancellations, a point where this derivative is big, then you produce a small interval where this derivative is big, where you can produce cancellations. The point is that you want to compare the L2 norm, which is an integral, the L2 norm of the iterates of the twisted transfer operator with this same integral in smaller sets where you see the cancellations. And this is essential that the big balls where you see integration, where you see the composition of your phase space is comparable with measure in smaller sets. That's where the feather property plays a key role. But for these Gibbs measures that appear naturally in the context of hyperbolic flows, you don't have that property. And it's actually very easy to produce counterexamples for the feather property. So what we did is, it was a different thing, is that instead of trying to compare a ball, the measure of a ball with the measure of doubling its ball, in order to compute this integral and to prove that this L2 norm cancels or decreases in norm, what we prove is that we subdivide the phase space in cylinder sets. And inside of cylinder sets, we try to find cylinder sets where we see cancellations. So at this point, it looks everything great, except for the fact that in general, the cylinder sets, they don't have the same size. So even though we are not working with SRB measures, there is a geometric aspect that appears here, and the geometric aspect is placed here, which is the same of saying that in any ball of a certain radius, we can find a sub-ball where we have cancellations. But this means that if we want to understand what happens under the integration, we need to understand geometric objects and how to combine these two ideas, one that comes from the Gibbs property and cylinders with things that are geometric as balls. So what we did is that given a finite Markov partition for the piecewise interval map, we determine estimates for the diameter. Well, it's easy. The diameter always contracts by the least possible expansion to -1, and there's also a lower bound. So you can always find an inhomogeneous Markov partition. So for each point, you choose the hitting time, you choose the stopping time, which makes him to have a certain size. And then within this size, which corresponds to these big balls here, you just need a deeper finite amount of iterates so that cylinder is contained in one of these balls. So you use the Gibbs property to compare measures of cylinders with measures of subcylinders, which are obtained from it at a finite number of iterates. And this is where you use the Gibbs property and how you replace this feather property by a different geometric constraint. In order to do so, we still need to compare balls. This is where conformality came, dimension 1. It could be higher dimension, but under conformal assumption. And there is still an issue, is that we need to cover by balls of a certain size, and that's why this argument works for piecewise expanding with finite number of iterates, finite number of domains. And some of the questions that pop up, one is the conjecture of Gouëzel, which is still open in dimension higher than 3, and in dimension 3 is still not known for C2 flows, it's just for C infinity. And the second condition is whether the conditions by Araújo and Melbourne are satisfied or not for most partially hyperbolic flows to study decay of correlations for such flows. That demands constructions of Gibbs Markov structures. There are some recent work with Ian on this direction, and the final one is whether this kind of strategy can be pushed to deal with piecewise expanding maps with countable number of domains, as for instance the Gauss map. This is the natural model to deal with Lorentz attractors, and a positive answer to this would lead to be able to show that the Lorentz attractors mix exponential fast with respect to other equilibrium states rather than SRB measures. So these are three directions of that are probably very interesting for the future. So thank you very much for your attention.
Thanks, Paulo, for this first talk. Are there questions, comments? There are many clapping hands arriving, but are there also questions?
I have just a comment, maybe.
Please.
Claudio, can you hear me?
Yeah.
Hi. Thank you, Paolo. I just have a comment about the transversality properties. Sorry, maybe you said something about it, but sometimes I lost the connection, so I couldn't hear everything. So about the transversality property that you described, used by Batterley and Bohr, yes, this one.
Yeah.
It comes from Tsuji's work, right?
For generic endomorphism, yes. Thank you very much.
Yeah, for genetic endomorphism. Right. Yeah, I just wanted to say that this argument of transversal unstable cones works also not in a Q-product fashion. Because just to say that this transversality argument works also outside of the skew product framework.
Okay.
Yes. And so it's interesting that it's kind of something that is not really related to the skew product structure, but you can really give a generic assumption in the case of partial hyperbolic systems.
Yes, yes, you're absolutely right. Thanks a lot.
No, thank you for the talk.
Yeah, in this case, we are dealing with this skew product structure just because of want to deal with the flows. That's why they appear natural.
Yeah,
Thank you very much.
Are there other questions or comments? Maybe one quick one, if it's possible to have a quick answer, otherwise we discuss later. So I was curious about the speed of the decay of correlation. I mean, it can prove exponential decay, but it seems to me that basically you use still the idea of Markov partitions, whereas all the stuff from Liverani arrived also to obtain some faster decay of correlation. So is it possible that some ideas from the base, I mean, some faster speed, the decay of correlation from the base goes to the flow, let's say, in some way?
Okay, so the point is that you kind of need to combine both informations.
Yeah.
Because you can have the fastest discrete time dynamics that you prefer, but if you make it exponential flow by constant roof function, it's not mixing. Because
sure.
So the I don't know if I got the deep thought that you have in mind, but the uniform non-integrability is really essential in all this process. This is what is as a tool for mixing. But Can you?
Okay, let me make it simpler. So is it possible that in the cases where you got exponential decay of correlations, you could restrict to some smoother observables to prove a fast decay?
Okay, thanks.
Maybe it's possible. But, I mean, there are ideas or ways to prove these kinds of results.
Okay, yes, I've seen kinds of approaches like that, but I haven't thought about them actually. Actually, I was my recent thoughts were in a kind of transversal direction, which is not using the structure of suspension flows and being able to deal with less smooth observables in some sense, but not very fruitful for the time being.
Okay, so thanks again. And maybe we make a couple of minutes break before Nicola's talk. Thanks again.
So thank you.
Okay, so we start again. So it's a pleasure now to introduce the second speaker for the day, and Nicola Bertozzi from the University of Pisa, just in the other building. And he will talk about exponential decay of correlations for two families of suspension flows over non-compact spaces. Please.
Actually, I'm in the same building, so okay. So thank you for inviting me. It's really a pleasure to give a talk for the DinAmicI seminar. I'm going to show you a couple of results from my PhD project in collaboration with Paulo and Claudio. As the title suggests, I'm going to talk about mixing and decay of correlations. Now here, Paulo told us a lot about decay of correlations. Just let me remind you that the correlation function is a way of formalizing the mixing of a system, meaning that we compare couples of observables, and if the function decays to zero, then we have mixing and the observables become asymptotically independent. And it is interesting to investigate the rate of decay of the correlation function, since it's a nice indicator of the chaoticity of the system, meaning that if we have a higher speed of decay, then we reach a high level of complexity in a shorter time. That's exactly what we will do. Now, the talk is in two parts. The first part, in each part, we will see a specific class of mixing flows, and we will establish exponential rate of decay of correlations. So let's start. The first one starts from the geodesic flow on the modular surface, which is a quotient of the usual hyperbolic plane. Here in red, we have a fundamental domain. The full blue lines represent the flow. It's a quotient of a typical geodesic on the hyperbolic half plane. And well, we know from Marina Ratne's work from 1986 that this flow mixes exponentially fast. And she exploited the nice algebraic structure of the unit tangent bundle of the modular surface. Then 12 years later, Chernoff raised a point that is, can we show the same results using a purely dynamical proof? Indeed, this would highlight the intrinsic properties, dynamical properties of the system, rather than focusing on the special algebraic environment, possibly leading to generalizations. Dolgopyat extended Chernoff's ideas and set up a method for proving exponential decay of correlation for a certain class of anosov flows. Why should we bother? Well, the fact is that the method here cannot be directly applied because, as Paulo told us, the method requires a compact phase space, while here the modular surface is not compact. But in this work, we managed to work around this obstruction and actually find an alternative proof of this fact, adjusting the method by Dolgopyat. So first, let's recall what the ideal setting for applying the method would be. Paulo told us, but here we have some sort of special case. Let me remind you. Basically, we need a compact space with a countable open measurable partition on it, a sufficiently regular function f, which has to be full branch and uniformly expanding. Just to fix ideas, think of a map like this one. We have the typical expanding shape. Here we admit countably many branches. We know from theory that these kinds of maps preserve ergodic probability and ergodic probability mu. Okay, so next we add a second component, which has to be compact too, with a map G acting on it as a contraction. And together, F and G define a hyperbolic skew product T, where hyperbolic clearly stands for the expansion and contraction behavior. Skew product is that because the first component of T is F, which only depends on the unstable component on X. We also need probability nu, which is preserved at T with a regular disintegration over mu. Just think of a measure on the whole blue region, which projects on the first component becoming mu, and which can be divided into many measures, each which with support on each vertical fiber. So we have our base system. Let's construct a suspension flow. So basically, we start from each point xy on the base, and we start flowing vertically until we reach a roof function R. At that point, we just pop out from the base at the point T of xy, and we simply go on like that. Now, as Paulo told us, this roof function has to satisfy a bunch of regularity properties. Now here in the picture, it's just an oversimplification. In particular, we are interested in uniform non-integrability, which is the conditions for which the roof cannot be represented through cohomology as a piecewise constant function on the partition elements. This indeed was first identified by Chernoff as one of the key features for fast decaying correlation functions. And so basically, if we have a suspension flow with all these properties, we can assert exponential decay of correlation. So why isn't it working for our contest for the geodesic flow? Well, first, let's make it a suspension flow. We do this by taking a Poincare section, so we only account for the moments the flow crosses this green vertical axis. We obtain the Poincare section, the first return time, and then, thanks to the work of Claudio and Alessio and Stefano Isola, we can find an explicit representation of these maps, which translate into a suspension flow with these features. So we have a base map, P, acting on couples of real positive numbers as a skew product with two branches defined by this F0 and F1, basically. We have a measure M, which is preserved by P. It's ergodic, and in this case, it is infinite, but it gives finite measure to all the vertical fibers, the vertical stripes, which are away from the vertical axis, and in the first component, away from infinity. Finally, we have a roof function, rho, which has this logarithmic expression, which involves the components of the map P and their derivatives. Note in particular that this roof function has finite integral with respect to M. So at this point, we can identify those key ingredients of this transformation and try to generalize them, because it is not necessary to work on this specific flow here. There are some basic features which we can exploit to define a whole family of suspension flows and work in a more general setting. So how can we do that? Well, if we pay some attention, after some time, we observe that basically almost everything depends on the first component map F. So let's have a closer look. let's say the hat has this kind of shape. So we have two branches. The first one increases from 0 to infinity as we approach 1. It is convex, and it has some technical regularities, which I will skip for simplicity. Just observe that here at 0 we have slope 1. The second branch is just translation of the identity. And this is roughly all we need for defining our family of suspension flows. And where is the conflict with the standard assumptions? Well, first of all, we are in a non-compact space because both first and second components are defined on unbounded domains. Then the measure, as we saw, might be infinite. The slope equal to 1 here produces rates of expansion and contraction which are not uniform for the first and second component. And also the root function might clash with this standard hypothesis. So why should we bother now? Well, the fact is that we can try to work around this obstruction by looking at the system from a different perspective. How can we do that? So let's keep focusing on this first component. We see that basically the interesting dynamics only occurs in this first branch, since the second one is just a way of bringing the points back to the interval 0, 1. So we can we can skip this boring part and induce the system on the interval 0, 1. That is, we take a point in 0, 1, we compute the number of iterates that we need to come back to the interval, and then we produce another map, capital F, as the composition of small f tau times with itself. In this way, we obtain another map which squeezes the dynamics in a more interesting transformation, since first of all, we are in a compact space, 0, 1, and then we recognize the typical expanding full branch shape for the map. There is a problem, though, because here at 0, we still have slope 1, so that 0 is an indifferent fixed point, which produces a neutral behavior around 0. But we can fix this by inducing again on another interval, which is away from 0. In this way, we certainly obtain another map, which has a more complex combinatorics of its branches, but it satisfies all the wanted requests on the first component, so we are happy with it. At this point, since the first component is set up, we can repeat the procedure on the second one. In the process, we obtain another map p hat. There are some technicalities because this map does not exhibit uniform contraction in the second component, but we can again induce or simply iterate again and obtain another map p tilde, which now has the uniform contraction on the second component. Now let's stop for a moment, and because we need to ask, are we really allowed to look at these induced system? I mean, we may obtain something on this induced system, but who tells us that we can recover something on the original system? Well, the fact is that inducing produces suspension flow, which in some sense is an accelerated version of the original one. And in particular, we can find a semi-conjugacy, which guarantees that if we witness exponential decay of correlation in the induced system, then we can recover exponential decay of correlation also on the original one. And so we can reduce to the accelerated version. So if we come back to the study of this base system, we see that the second component acts as a strong contraction because it sends all the unbounded vertical fibers into intervals which have length less than 1. So it's pretty strong. But in some cases, these small intervals may run all over the positive real numbers. So we don't have compactness. With induction, the induction procedure, we managed to trap the first component in a compact region. But the second one was not that lucky. So at this stage, the only thing we can do is go on with our analysis, ignore this problem for the moment, and then see if we can do something later. So we have everything on that we could say on the base map. The second ingredient is the roof function. First, we can simplify our roof function using cohomology, because I don't want to give too many details, but basically, cohomologous roof functions yield dynamically equivalent suspension flows, because it's sort of taking a change of variables or modifying the cross-section to the flow. So since we can prove that we have another roof function, rho bar, which is cohomologous to the first one and has a simpler expression, we can just simply get rid of rho and work with this new function. Then remember that this function is defined on the original system, base system. That means that we have to update it following all the procedures, first inducing, second inducing, and then iteration. In the end, we obtain this R tilde, which depends both on the unstable and stable component. While the standard assumptions for the roof functions wants us to have a roof function which only depends on the unstable component. Luckily, the so-called Bauern's trick comes to help, because we can define this series which yields a cohomology between R tilde and another function R, which only depends on X, because this Y prime is fixed. Now, certainly we have to check that this series is well-defined and convergent. I will skip these computations because they are a lot, they're a bit technical, but basically everything works fine thanks to the uniform contraction of the second component and the nice form of the roof function. So at this point, let's see what we have. Now, the first component works perfectly fine because we have compactness, regularity, and expansion, uniform expansion. Also, the roof function is okay. Now here, in order to check exponential tails and uniform non-integrability, we required a bit of work, but the nice properties defining the systems helped us recovering these properties. As for the second component, the only missing piece is that we don't have compactness. Luckily, we can still overcome this obstacle. How? Well, first we proceed as in the standard setting, in the standard case. So we project the flow onto the unstable component, for which we know that we have all the right check marks. So this projected flow satisfies all the hypotheses that imply exponential decay of correlations. Then we look at the correlation function for the whole system. We can split it into two terms. One depending only on the unstable component, so everything is fine. The second one is the real deal. Now, in the compact scenario, uniform contraction is sufficient here to reduce to the unstable component. But in this non-compact case, it is not sufficient. That is, if we do not have a strong contraction. We have a strong contraction because the vertical fibers are squeezed into intervals with length less than 1. And it turns out that this is sufficient to carry on the procedures, the typical procedures, and finally obtain the exponential rate of decay of correlations for this system, the suspension flow with base P tilde and roof function R. So to summarize, we took the geodesic flow on the modular surface. We generalized it to a family of suspension flows, and then we modified a bit the method by Dolgopyat and proved the exponential decay of correlations. In particular, we recovered an alternative proof of the result, the first result by Marina Raffner, employing only basic tools from dynamical systems theory. Okay, this is what we wanted, and this ends the first part of the talk. In the remaining time, I would like to show you shortly another nice application of this Dolgopyat's method. Now, up to now, we've been working in a specific geometric environment, but as Paulo told us before, there are ways of looking at the systems from a more abstract perspective, such as the symbolic perspective. Now, we know that we can, in some cases, encode flows through Markov partitions and define suspension flows over Markov subshifts of finite type, which describe the original flow in this more generic framework. In particular, Dolgopyat took advantage of this and showed that on this kind of flows, if the root function behaves well, then the method can still be applied and recover exponential decay of correlations. So this works when the manifold here is compact. In the first part of the talk, we worked on manifolds, basically, which were not compact. So what is happening here in the non-compact case? Well, the coding idea is basically the same, but in general, it will produce infinite Markov partitions, which yield an infinite alphabet, that is, infinite symbols for our shift. So it became interesting to look at these kind of symbolic flows and investigate whether we can formulate some conditions that imply that the method by Dolgopyat can still be applied in some way. And this is what we did. So let me recall the usual symbolic setting. So we have an alphabet, which of symbol or states, which is infinite here, countably infinite. We have the transition matrix with entries 0 or 1, which defines the set of allowed words based on whether two consecutive symbols have the relative entry of the matrix, which is equal to 1. Note that since we have an infinite alphabet, this space is not compact. And then we have the usual shift map. Here we have the one-sided shift because usually we can reduce to the one-sided shift. Then we have the usual definitions such as the cylinders, which are sets of words with a prescribed initial word. Their length is the number of symbols, prescribed symbols. For each cylinder C, we can define the inverse branch of the map, some iteration of the map, which is basically that action which touches to the left of our point omega, the prescribed word A1 to AN. Note that the domain here might not be the whole space because we have to be careful about the transition here from AN to omega1 to be admissible. And then we define the usual separation time metric and the Lipschitz functions in this setting. Now, we want to introduce a measure theoretic perspective. So we define a continuous potential with its pressure P phi. Phi is the potential. In order for phi to be well defined and for all the constructions based on phi to be well defined, we ask a couple of requests on phi. That is, we wanted to have finite variations and to be summable, meaning that we have some control of phi on the cylinders. Then we find the usual Perron-Frobenius operator as usual, so with the usual formula. Okay, at this point, we have all the underlying symbolic setting that we wanted. Let us see what are the dynamical conditions on the base that we require in order for the method by Dolgopyat to be applied. Well, first we ask for topological mixing. And then a technical request, that is the transition matrix must have for each row at least 2 non-zero elements. Now, this does not affect generality that much, but the main set of conditions is the following. Basically, these are the consequences of Gouëzel-Perron-Frobenius theorem. That is, we have an eigenmeasure nu for the operator, an eigenfunction h phi for the operator, which is Lipschitz, is normalized so that its integral with respect to nu is 1. It's bounded away from infinity and from 0 from above, from below. Then the measure mu defined by this density is T invariant and ergodic. These are assumptions. Now, note that we are losing the parallelism with the first part of the talk, because here we are working in a probability setting, while in the first part we allowed to have infinite measures. Now, the fact is that this is our first attempt to study these kind of systems with an infinite alphabet. So we decided to proceed step by step, and we started working with a finite measure setting. Okay, the last condition is the convergence to equilibrium. That is, if we normalize the operator, then its iteration on a function f must converge exponentially to the average of f in Lipschitz norm. And okay, so these are our requests. Usually we like to work in settings which satisfy these conditions, because usually it's the Gouëzel-Perron-Frobenius theorem to hold which implies these conditions. But since the infinite alphabet case might be tricky and has some hidden subtleties, we decided to list these abstract set of conditions. If we want a more concrete point of view, we can work in the so-called big images and preimages property, which is a way of introducing again finiteness in our symbolic infinite case. So this is the definition of this property. Just let me show you with this example. Basically, we are asking that we have a finite set of states. Here, there would be A2, A3, and A4. So that if we choose any state, let's say A5, then we can choose between one of the columns in the related to the symbols in this set S, so that the entry related to A5 and one of these columns has 1 as an entry. The same has to be true for the rows, so that if we look at the column A5, we must have one of these 2 rows for which we have a 1. And in this case, it would be A3. So this is a more tangible way of displaying a nice property which for which Gouëzel-Perron-Frobenius theorem holds, so that all these abstract conditions that we defined earlier hold. Now, let's get back to the more general case. We define the base system. The root function is just sufficiently regular, let's say piecewise Lipschitz. It has exponential tails, meaning that we have some control on its growth. And then we must state the uniform non-integrability condition, the one Paulo told us before. We can state it using this function capital psi, which involves the Birkhoff sums of the root function and 2 cylinders. Then the request is that if we compare differences of this capital psi on 2 different points with their distance, then this infimum must be greater than a certain specific positive real constant for a sufficiently large n0. Now, this might be a bit messy, but informally speaking, this guarantees that this function psi is as, let's say, irregular as it can on a large enough set. And it implies that R is distant enough from being piecewise constant on the partition elements, which is what we wanted to avoid in order to have exponential decay of correlation, as we saw also in Paulo's talk. So now we are ready for the main results. The protagonist here is the family of twisted transfer operators. The twist refers to this factor here, which involves a complex number S and the root function R. But it also involves the transfer operator. If the real part of S is close enough to 0, then this family is continuous, and it produces a continuous family of eigenvalues lambda sigma and the eigenfunction f sigma, where sigma is the real part of S. These values, these objects are uniformly bounded by those values at 0, which we know are the eigenvalue and eigenfunction of the normal twisted transfer, of the normal transfer operator, since L0 is our usual Ron-Frobenius operator. Then we proceed to normalize this operator for better computations, and our main result is the following. Basically, we have a contraction result on a suitable adapted norm of the iterations of the operator. This norm is adapted because it, for simplicity, depends on the imaginary part of S. But the fact here is that the main result is important, this contraction, because it's a crucial step in Dolgopyat's method. Because once we have this contraction, then the method flows as usual, and it implies exponential decay of correlations for the suspension flow defined in this way. Now, in order to obtain this contraction, basically the procedure is analogous to the finite alphabet case, but we have to be careful and adjust the arguments. So let me just focus on the obstruction, on the obstacles that we had in this case. In the finite alphabet scenario, we had two really important ingredients, which were compactness and the Federer property, which here is stated in a different way. Let's say it is a uniform bound from below on the measure of nested cylinders, let's say, but the rigorous definition was the one that Paulo gave us before. With these two underlying fundamental ingredients, we achieve a contraction of the normalized twisted transfer operator in the norm L2. And then we can upgrade it to the contraction in the norm, the adapted norm. In our infinite alphabet case, we do not have compactness, and also Federer property doesn't hold. That's because we have basically an infinite number of cylinders, but their union is the whole space. So the whole space has measure 1 because we are working with a probability. That means that from a certain cylinder on, the measure of the cylinders must decay to 0. And this prevents us to find this uniform bound from below. So what can we do at this point? Well, we take from some ideas from the big images and pre-images properties, meaning that we can try to introduce some finiteness and work in this safe and finite environment. How? We use an approximation argument. So let us fix some constant epsilon and delta. Basically, if we have cylinders of n, we list all the cylinders. We know that they cover the whole space. So if we truncate this list at a certain n delta, we can make sure that the sum of their measures exceeds a certain value delta. Then we restrict our study to these sets, this finite set of cylinders, And so we can find uniform bounds depending on epsilon and delta, and some sort of analogous of Federer's property that allows us to find this contraction in L2. Well, it's not really a contraction, it's a weak contraction, because here we have this term plus epsilon. Let me just mention that if we are in the BIP case, the big images and pre-images property, this epsilon does not show, so we have a strong contraction. But in the general case, we only achieve this estimate. But if we tune epsilon in a nice way, we can still recover the nice strong contraction on the adapted norm, so that in the end, we finally obtain our goal, our main result, that leads us to exponential decay of correlations for this symbolic flow. And this is basically what we wanted to have. This was another application of Dolgopyat's method, also in this unusual setting with infinite many symbols. And that's it. That's what I wanted to show you. Thank you.
Okay, thanks, Nicola. Other questions again or comments?
Maybe I have one.
Yeah.
So in this second result that you're presenting, so the roof function is assumed to satisfy a set of conditions which are similar to like uni, etc. And this is satisfied for generic roof functions, or is that a generic condition on the roof function?
Sorry, what do you mean by generic?
Like a bare generic set of roof functions that satisfy this condition?
Oh, okay. I didn't think about this issue. I just basically took those conditions that allow us to infer what we wanted, but then the study stopped here. But it would be a nice investigation for the future to see whether these roof functions can be part of some larger class or I don't know.
Okay. If I remember this second paper of Dolgopyat in 98, he proves this exponential decay for suspension flows, but he also claims something about that typical roof functions to have the exponential mixing. That was my question, basically.
Okay. Well, as you can see, this work is based on that on that paper, basically.
Yeah, sure.
So I didn't think of that part. I just worked on the exponential decay property. But yeah, it
at
can
some
be.
moment you make a finite approximation.
Sorry?
At some moment you make a finite approximation. Yeah.
Finite approximation.
You approximate by a finite number of symbols, if I understood correctly.
Yeah, that could be. Thank you.
Okay, thank you.
Yeah, there are other questions. Okay, let me thank Nicola again. You can go again.